pressure versus temperature. And this is the standard three-phase diagram. Okay, so I can have solid, vapor, and liquid. And then there's two of these lines here. Okay, and this one represents a pure substance, say water, copper, whatever it might be, gold, a pure substance. And then when you freeze it, okay, when it becomes solid, liquid to solid, it contracts or expands. It expands when freezing. So not all materials expand when they become. So when they're liquid, when they become solid, they get smaller. Now, water is one of those unique substances that actually, when you go from liquid to solid, it expands. As a consequence, our lakes don't freeze solid. If it was the other way around, if you were up in northern Minnesota where I grew up, you would see that all the lakes would be frozen solid in the winter. If it was the other way around, because all the ice would go down, right? And it's colder up top than it is bottom, so you just get. So then you can get a layer of ice at the top. Right? Most materials do this; they contract on freezing. Okay, so this is pressure, and then this is temperature. So I could say pressure 1 atmosphere right here. And so if I'm at 1 atmosphere pressure, okay, 14 point something or 13 point something psi, or 101 kilopascal, or 1 bar. And then I go from absolute 0 Kelvin. Okay. And I'm going to be solid. And then at some point, right here, so we'll say water, just for the sake of convenience. Right here, because I'm at this pressure, I am going to make a phase transformation from solid to liquid. And so at 1 atmosphere, this is 273 Kelvin, so water at 0 degrees Celsius. And then I cross the line. Now, there's a meaning to the line. And you could see I couldn't draw a line without a width. Just pointing out that when I use my pencil, there's a width to that line. Then I increase the temperature at 1 atmosphere. And so then I heat up water from 0 degrees C, or 273.15, right, Kelvin, up to 99.93 degrees C, a little less than 100 degrees C, where you have phase change. So we'll just put 373 here, and that's actually pretty close, 373, and this is 273.15. Anyways, so, and then I go from liquid to vapor, so I boil. But you can see here again that when I drew this line, there's a width to it. So I just want to point out that when I drew the line, there was a width to it. And I'm going from liquid to vapor. Okay. So let's just focus on this line right here. I can change the pressure, and I can go to a different pressure, and say here, and I can go right through this, I can go right through that point there. So in this case, I would have the pressure set up perfectly. And then I think this is like where you go from solid straight to, and then you have a point, and there's a size to the point, right, that I draw, and I have all 3 phases that coexist, and then I'm just vapor. And I could go up here really high. I could draw another line way up top. I could do something like this. And then I would have at really high pressure, I would transform to liquid at a much lower temperature. And in principle, I would go from liquid to vapor at a much higher temperature. And you can see once I become liquid, in some ways, once I did that, because I was above the critical point, once I went to solid, I went to a phase where I would be, it would be another form of material, because I'm above the critical point. So it's really hard to define that once I'm to go from solid here and I go to liquid, it's hard to say that I'm actually liquid, because I was above some critical pressure. So let's just draw a line that goes like this. Now it's a little more well defined. So now I'm solid, I go through a phase change, I become liquid, and then I go up to the critical point, and then after I increase the pressure a little bit more, so right here would be some critical temperature, and I have my critical. And so once I go at any temperature beyond the critical temperature, I'm schizophrenic as a fluid, right? I don't know whether I'm liquid or vapor. And any temperature below, I can still say that I'm liquid phase. So basically I go from liquid phase to liquid and solid phase at the critical pressure. But anyways, you can see that I can take this, and of course I could do the same type of thing. I could say constant temperature increases in pressure, and I could get some, and that would be pretty interesting, right? So I start at really low pressure at 0 degrees C. I'm basically vapor. Then I go straight to solid, and then I go from solid to liquid. Okay, and so we were talking everything with a material that contracts on freezing or expands on freezing. We could have it here, and then it would look a little bit different. And you can see this line here. It's after, everything's after this triple point. Okay, so let's go to this part right here on this line. So as I cross it, when I cross it, there's a width to this line. And so what I have here is a substance that expands on freezing. If this is 1 atmosphere, and now here's my bell curve. Okay? Now, as I increase in specific volume, okay, that in some ways I can draw a temperature isotherm, right? And so I can have one at 50 degrees C here, and I can have one at 100 degrees C here. So if I'm at constant pressure, that means anywhere along this line, I can increase the temperature. So this is as T increases. So like right here, this one represents 50 degrees C, this point right here. And then this point here represents 100 degrees C. I could have another line here that represents 20 degrees C. Okay? So 1 atmosphere, I shouldn't put 20 degrees C. I should put minus 20. So I stay solid. So we'll say minus 20 degrees C. So I have this, and so at minus 20 degrees C, I'm solid phase. And then at 50 degrees C, I'm liquid phase. And then when I'm at 100 degrees C, and you can see here that there's some width, solid and liquid. So I go from solid and liquid to liquid. So really I'd want this one to be C, but anyways. The slope of my isotherms are not, I should have had them steeper. These isotherms should have been steeper, but anyways. So if I put this as 0 degrees C, you can see that I kind of come through this region here. So at 1 atmosphere, 0 degrees C, you have phase change, right? You go from solid to liquid. And then when you do that, there's a width associated with. Just like on this bell curve, at 100 degrees C, this is my line for 100 degrees C. And at 100 degrees C, 1 atmosphere, I can be all liquid, saturated liquid. I can be a mixture of liquid and vapor, right in here. Or I can be 100% vapor, saturated vapor. And so there's a width of this bell curve tells me kind of a concentration at 100 degrees C, 1 atmosphere. You know, the energy required to it. But anyways, I have this width. This area right here corresponds to this area right there, the width of that line. So as I cross this line, I go through a bell curve. I go through this part of the bell curve. So this bell curve in many ways represents a line through here. So if I'm at lower temperature, say this one, for lower pressure, and I go through, that means I'm further down in this bell curve. And if I go up to this P critical, and I come across, okay, that means that I came across right here. And so once I did that, there was no width to the bell curve because I went through at that point. So you could think of as a bell curve, I could draw a bell curve on here. Or if I drew this line, right, to better represent, it would be thickest at the base and then it would have no width at the top. So if I could draw a really nice line where you could see the bell curve and you'd use a magnifying glass and you'd zoom in, you would see that it would look something like this. This whole line. And likewise, this line would have some width to it too, but this one would be more constant. In fact, it does get a little wider at the top. So, on these 3-phase diagrams, you have these lines that separate the phases. There's energy required to cross the line. Kind of the width of the line, or the width of the bell curve, corresponds to that extra energy to cross the line, to change phases, to switch teams, however you want to look at it. Okay, so that was kind of a side thing, but I wanted to point out, yes?
For the solid and liquid, can you go down to the bell curve?
Mm-hmm.
Thank you. For the solid and liquid phase, would that isotherm also be like?
Yeah, I drew these. These are steeper up.
But would it be flat like at constant pressure when it's going through that solid and liquid like it is for the liquid and vapor phase? The isotherms?
Would they be flat going through here? Yes.
Okay. I couldn't tell.
Yeah, I didn't draw it right.
Alright.
But yes. So this one here at 0 degrees C, it should go up, be flat, and then go up again. Let's just draw an orange. And let's do one right here. Comes across, comes up, flat, and then comes up. It should be flat. It should come up and then it should be flat again. Because you're going through phase change, and by definition, for phase change, you're not, you don't go through, you don't have that equilibrium phase change, there's no change in temperature. So if you take control volume that goes from liquid to vapor, that control volume in that process stays at constant temperature during phase change. It doesn't mean that the other ones around it might not change temperature, because if for phase change you need heat transfer, right? So you could heat up or cool down your neighboring control volume. But yeah, it should be flat here. So I guess I should have, on this one here, I should have did something